All right, let's take a look at operations with radicals. So we're just building upon simplifying radicals and looking at some more complicated situations that involve those lovely radicals. So just before we get to the actual lesson, the sheets there, let's remind ourselves of just some basic old algebra. If you had 2x times 3y, what do? Well, I'm sure you know this. Multiply those numbers out in front. The x and the y, you can't combine them, so it's just xy. What if you're adding like terms? This is way back to grade 9. 2x plus x. Well, they're like terms, so you just combine them together and leave the x as is. So 2x's and another x make 3x's. What if you're multiplying a variable into some brackets? Well, just in this case, we're distributing it in. So x times 5 is just 5x. What's x times x? Well, that's just x squared. Hopefully this is all familiar looking. What's going to happen, though, when we're dealing with radicals? We can, in a sense, almost just think of it like one of these variables. So however we treat these variables, treat the radicals as the same. We'll see that as we go through the examples. So I'm going to put up some examples here. You can see they look really similar to those variable ones. So 2 root 6 times 3 root 8. So again, multiply the numbers. So 2 times 3 is 6. The radicals, they're two different radicals, so we can leave them as separate. The one thing, though, unlike the variable version up above, we do have radical rules which allow us to combine root 6 and root 8. So in this case, root 6 and root 8, so, well, 6 times 8 is, I think, 48, if I can do math. And again, we always got to simplify. So that 48, how can we break that down? Well, that would be root 16, root 3. 16 is 4, so 4 times 6 is 24, root 3. Okay, let's take a look at the next one. So 2 root 5 plus root 5. So again, just pretend that's like your x. You're in a sense collecting like terms. So we actually have, well, 3 root 5s, just like we had 3x's before. And if you had two different radicals, like if this was, I don't know, a root 6 instead, well, root 6 is not the same as root 5, so you couldn't do this kind of thing. And lastly, we got a root 3 in front of some brackets, so distribute it like we distributed the x. So root 3 times 5 is, well, 5 root 3. Root 3 times root 3, well, it's just those two roots multiplied together as in root 3 squared, which in this case we can simplify, unlike the x squared up above, to just 3. So there we have it. So it ends up being very similar to what you've done with just regular old algebra. There's just a little bit of extra nuance where you can sometimes combine your radicals, but sometimes you can't. So just be careful. Let's continue on. So 2 root 6 minus 2 root 24. So this is a situation where you have different radicals. You cannot combine them. So if you can't combine them, you might think, okay, we've got nothing to do. But maybe we can simplify these individual radicals. So can root 6 be broken down any further? No, there's no perfect square that divides into that. But root 24, well, take a look at this. Root 24 is, well, just root 4 times 6. And so let's just simplify that. So 2 root 6 minus 2, well, the root 4 that's in front. I'll break it apart. I'll do this in 2 steps. Of course, you could do it in 1 if you wanted to. Root 4 is 2, and 2 times 2, we can combine that together to make 4 root 6. And look at that, we now have root 6 and root 6. They are, in a sense, like terms. So because of that, we can combine them. You can see over here, like radicals can be added or subtracted into a single term. So 2 minus 4 is just, well, negative 2 root 6's. So there we go. Let's continue on. So we've got brackets. Just brackets. Just distribute things out. So in this case, the number 2 multiplies by everything in the right bracket. So we've got 2 times 2, and then minus 2 root 5. Again, got to take into account that sign. And what about the root 5 here? So the root 5, multiply that by 2, multiply that by the other root 5. So we're going to get plus 2 root 5. Root 5 times root 5 is, well, root 5 squared. So it's just going to turn into 5. So minus 5 when we take into account that sign. And if you take a look at this, we can simplify this a little more. So the 4, or 2 times 2 turns into 4. And minus 2 root 5 and plus 2 root 5, they cancel each other out. So we're just left with, well, 4 minus 5. And what's 4 minus 5? Just negative 1. So that weird looking bracket thing simplifies all the way down. And really, if you take a little bit of a closer look at that, that's very similar to a difference of square, where those middle terms cancel out. But now instead of just like a regular old number at the end, it's a square root. But it, in a sense, is that same thing. We just end up having that square root squared. So in the end, it was the number 5 instead of like some sort of number squared at the end. And that's going to be very important later on. Okay, so let's put this into practice into some kinds of questions that may be similar to what we've done in like quadratics, those kinds of units, and how we can apply these rules. So we're solving for x. We're leaving our answer as an exact radical. So we've got x squared plus 6x plus 1. Usually we try to factor. This one's not factorable, so we got to use that quadratic formula. And that's where you're going to get the radical coming in. So we're going to have negative 6 plus or minus the square root of b squared, which is 36, minus 4 times 1 times 1, all over 2. Well, 2a, but there's just a 1 for the 2a. Let's simplify this a little more. So negative 6 plus or minus 36 minus 4 is, I think that's 32, all over 2. And so here's where we have the 32. So I'm just going to do this off to the side. You could do it just within everything there, but let's simplify this. So 32, well, that's the same as, I'm just thinking a little bit here, root 16 times root 2, or 16 times 2. And root 16 is 4 root 2. So now we can go back into there. Let's replace that root 32 with negative 6 plus or minus 4 root 2, all over 2. We're not even done yet, because what works out really nicely here, we're dividing things by 2, and the numbers are on top are actually divisible by 2. So you can just divide each of the individual parts. So negative 6 divided by 2 is just negative 3. Still plus or minus. And when we're dividing the 4 root 2 by 2, you just need to divide by the coefficients. So 4 over 2, what is that? Well, that's just 2. So negative 3 plus or minus 2 root 2. I'll just add a note here. So divide 2 into both parts. And there we have it. This is our final answer. And then you could look at it, of course, as the positive answer and the negative answer. But that's simplified in the simplest way. All right, continuing along. So we want to find the equation, let's say, of a parabola. We've looked at these kinds of questions, looking at quadratic families, how we get those equations. We've got a 0.1, negative 1, and we've got a root of 2 plus or minus root 3. I mean, actually, it's 2 roots. So how do we start things off? Well, if we have roots, we should think instantly factored form. So let's set up the general equation. So f of x is equal to some multiple. I'll use a. You could use k. Again, doesn't matter. And then we're just going to set it up in factored form. So subtract as an x minus whatever the factors are, or whatever the roots are. We just have to be careful because it's made up of like 2 parts of the root. So 2 plus root 3 or 2 minus root 3. So to start off with, I'm just going to write that root inside brackets because we're subtracting that entire thing. Same thing with the other one. So those are the two roots. And let's just do a little bit of simplification. So if you have that in brackets and you're subtracting it, well, that's the same as x minus 2 minus root 3. Just distribute the minus sign in. And on the other side, we have x minus 2 again, but now plus root 3. Looks a little messy, but we know how to deal with roots now, so we can continue tackling this question. So that's part 1. Part 2 is let's make use of this point. So we know that if we're finding the specific equation, we just need to substitute in that point into our function. So f of 1, what is that going to be equal to? Well, that's going to be a times, just use what we had up above, 1 minus 2 root 3, 1 minus 2 plus root 3. Looks messy, but it's manageable. And we know in the end, that's going to be equal to negative 1. So let's simplify that bracket. So 1 minus 2, that's just negative 1 minus root 3. 1 minus 2, well, again, negative 1, but plus root 3. And you might see this looks kind of similar to the above where it's almost a difference of squares there. Plus and minus the same numbers. So let's just multiply it out and see what happens. So we're going to have a times, well, negative 1 times negative 1 is 1. So that's that. And then we have, well, negative root 3. Starting with the negative root 3 times negative 1. Well, that's going to be positive root 3. And negative root 3 times positive root 3. Well, root 3 times root 3 is 3, so minus 3. So simplifying that all in the brackets, we got a 1, we got a minus 3. And, well, lo and behold, the root 3's cancel out. So 1 minus 3 gives us just negative 2. That's it. And this is now a nice, easy equation to solve. A is equal to negative 1 over negative 2, which is just 1/2. So therefore, the function is actually just f of x. Still looks a little messy, the actual function, because of those roots, so it's still going to be x minus 2 minus root 3. But we got a nice a value through all of that. And there we have it. That's our function. So just be careful when you're initially creating that factored form. You're subtracting that entire part when you're going through and setting it up. Okay, let's continue on to just one actually pretty important topic. So what's important in math is we like to have good mathematical form. Things like, I don't like negatives in the denominator. I'd rather have that as, well, negative 3 over 2. Another thing we don't like is we don't like having square roots in the denominator. It's just a matter of form, but we do want to figure out how can we change the form so that it's in our preferred way where there is no square root in the denominator. So let's see how we can do that. What we're going to do is we're just going to take advantage of the fact that a square root multiplied by itself, well, it just makes the square root disappear. So for example, root 2, if you multiply that by root 2, well, root 2 times root 2 is just 2. But you can't just multiply the bottom by something. If you want to keep things the same, you have to multiply the top. Because root 2 over root 2, we just take a look at just that part, well, that's just 1. Multiplying something by 1 doesn't change anything. So that's going to be the idea, is we can multiply these fractions that we already have by a fraction of our choosing that's very nice in particular. That'll make that square root disappear. So now, what happens is when we're multiplying fractions, we have 1 times root 2, so that'll just be root 2. And on the bottom, root 2 times root 2, we chose that specifically, which disappears. So that's root 2 over 2. And that's going to show up a lot, actually, when we get to trigonometry somehow. We'll get to there later, though. Okay, we have 3 root 5. Again, try some of these on your own first. I will always just continually be going through the questions, but feel free to pause the video at any point. So with this, again, we want to make that root 5 disappear. So, I just multiply it by root 5. Can't just multiply by root 5. You need to, in a sense, balance it out. Kind of like when we were completing the square. When completing the square, you always like had that, oh, plus the one number minus that same number. Here it's multiply by the square root and have it on the top of the fraction as well. Okay, and on the top, 3 times root 5 is just, well, 3 root 5. And on the bottom, root 5 times root 5, just 5. There we go. We've simplified that. So it's good. Things are working out. We can get rid of square roots. Oh, well, we thought so. But now we have some trickier examples. Because if you try to do this times root 7, let's just look at the bottom. Well, if we do that, again, we have to multiply the entire part. It would give you, well, root 7 plus, well, then the other root disappears. But you're still left with a radical there. So how do we get rid of that? Well, we need to return back to some of those previous examples. So let's scroll up for a moment. And let's take a look at this example here. We had 2 plus root 5 on the left here. When we multiplied it by 2 minus root 5, look in the end. We just got a single number. That's going to be the key. We can multiply this by a special thing. We'll see what we call it. And then with that special thing, we can make the square root disappear. So what is that special thing? Well, in a sense, think difference of squares. So let's say if I have 1 plus root 7, or if you had 1 plus x, or whatever it might be, if you're setting up a difference of squares, you'd start with the same first number and just do 1 minus the second part. And that becomes, when we multiply it, it's going to work out. This thing, this 1 minus root 7, we call this the conjugate. So the conjugate is the thing that we multiply another radical part, let's say, which will make that radical disappear. It's kind of that difference of squares part. So let's see it at work here. So 1 minus root 7. And again, can't just do the bottom. You have to do the top to balance things out. And let's work some magic. So on the top, 1 times 1 minus root 7 is, well, just 1 minus root 7. On the bottom, you have 1 times, well, negative root 7. As you get more used to multiplying by conjugates, you'll get more used to just canceling out the square root parts. So you won't need to necessarily write it out as fully as I am right now. You next have plus root 7 times 1, so plus root 7. And the last part, root 7 times root 7, is just minus 7. Because root 7 and the root go together and make it disappear. Because it's like squaring it. Okay, so we cancel out those roots. You're just left with 1 minus 7. So that will become negative 6. Oh, and again, I said before, I don't like negatives on the bottom. Let's just stick it on top. So if you move the negative from the bottom to the top, you can just flip the order of what's on top. And there you have it. This is now like as good a form as we can get it. No negatives, no square roots in that denominator. Okay, let's try that one more time. This time with 2 minus root 3. So first of all, the conjugate. This is what we want. This is going to be, well, start with this first number as being the same. And flip the sign of the square root. So 2 plus root 3. So multiply both the top and the bottom by 2 plus root 3. Okay. So the top, you actually have a 5 here, so you do have to do a little bit of work. So 5 times 2 is 10, and plus 5 root 3. Okay, on the bottom, this time I'm going to do it without writing out the full thing. So what ends up happening, just like when you had a difference of squares, what happens is, here I'll just draw some brackets, you square the first number in a difference of squares. So 2 squared is 4. Things cancel out in the middle, and you subtract by the last number. In this case, it's the root 3 squared. But when you square a square root, the square root disappears, so it just ends up becoming 3. So you just have 4 minus 3. And now when you simplify that, well, this one actually works really nicely. It's just 1. So that whole fraction just disappears. You just get 10 plus 5 root 3. That is our proper form. So make sure, check your understanding on those conjugate questions. Those are definitely some tricky ones. Rationalizing that denominator. All right, that's everything.